Well, we talked a lot about ideal gases, now we have to talk about real gases. So when we're talking about an ideal gas in kinetic molecular theory, an ideal gas has no attractions between gas particles. When the particles collide, they don't interact with each other at all. That's a requirement for an elastic collision. And the ideal gas also has a negligible particle volume. Real gases act very much like ideal gases under certain conditions. And standard temperature and pressure is one place where they do that. So here we have a graph showing the molar volume in liters of an ideal gas and of several real gases. So the ideal gas, we can calculate that, is 22.41 liters. And these other real gases are all pretty close. Some of them, like helium, nails it, 22.41 liters. Exactly the same within the sig phase. So at standard temperature and pressure, real gases act very much like an ideal gas. But when we get to a high pressure situation or a very low temperature situation, then they don't act like ideal gases anymore. So at low pressure, like 1 atmosphere, standard pressure, the molar volume of argon is nearly identical. But as we compress that gas, we increase the pressure, we're squeezing those particles together. As you get those particles closer and closer together, at some point, the size of the particle begins to become important, right? I talked to you guys about Wyoming, population of Wyoming. It's about the same as the population of Fresno, right? So in that huge state, 400,000 people, doesn't matter how big the people are, right? But you get people closer and closer and closer together. Let's go to an extreme. Let's talk about the small elevator that we have here. Been in that elevator? It's not very big. So there, the size of the people matters, right? So if you've got, we'll just stay with the running back and the linebacker. If you've got 10 running backs in there, they're going to fit okay. If you've got 10 of the 360-pound linebackers, they are not going to fit in that elevator. Maybe not even if they stand on top of each other, right? They're big, and in that small volume, the size of the people matters. In a huge volume where there's lots of empty space, the size of the people doesn't matter. The size of the gas particles matters when things start to get crowded. And so because the real gases do have volume of their particles, then they begin to deviate from ideal behavior. So this is what we see. Here we've got an ideal gas looking at the molar volume as a function of pressure and argon. And so up here in the 200 atmospheres, that's like crazy high pressure. 200 atmospheres, things are still behaving ideally. But as we continue to increase the pressure, we see that the molar volume of argon is larger than that predicted by the ideal gas law. That's because as those gas particles are getting closer and closer together, it's like, hey, I'm a big guy here, I'm taking up some space, and so the gas itself as a whole will take up more volume. Does that make sense? So at high pressures when things get squished together. Well, what if we want to calculate the volume of a gas at that high temperature? What do we do? Because it's not ideal anymore. Well, in 1873, Johannes van der Waals modified the ideal gas equation. And this is an empirical modification. So here's the ideal gas law. And at high pressures, the volume is larger. So he adds a factor. That factor is going to depend on the moles of gas and which kind of gas it is. So B is called the van der Waals constant, and it's going to be different for each gas. So that makes the molar volume larger than we expect. You do not need to memorize this. I just want you to be aware that there are equations that enable us to calculate that difference from ideal behavior. The other thing that affects ideal gas behavior is intermolecular attractions. At high temperatures, gas particles are moving very quickly, and we see that the pressure of a gas is nearly identical to that of an ideal gas. When we get to low temperatures, at low temperatures, what happens to the velocity of the particles? They go slower, right? Things slow down when it gets cold. And now when those particles are bumping into each other, they do so more slowly. All particles do have some attraction for each other. We'll talk about the nature of those attractions later. But there is some attraction between particles. And some particles have a lot more attraction for each other than others do. When the particles are moving very quickly, they don't have time to interact. They're going to just bounce off of each other and move on. When things are moving more slowly, though, and they collide, there's time for a little bit of attraction to happen. And so they're going to stick together a little bit before they go on their own way. Think of this a little bit like meeting people, right? If you're meeting people very, very quickly, just bumping into them on a crowded sidewalk or something, are you going to fall in love and have a relationship with somebody? No. You maybe don't even see them, you just bump into them, right? But if you're stuck in a situation where you're forced to interact with each other for a longer period of time, then the possibility of a relationship becomes more real, right? So there might be some attraction that would pull you together. So at low temperatures, the gas atoms can interact more with each other. They'll spend less time colliding with the walls, and so the pressure goes down. The pressure will be less than predicted by the ideal gas law. Here's a graph showing that. So here at low temperatures, the pressure of an ideal gas is higher than a pressure of a real gas like xenon, because the xenon atoms do have some attraction for each other. And as the particles are moving slower and slower, that interaction becomes more significant. At high temperatures, they're moving so quickly they don't have time to interact. So van der Waals also modified the ideal gas equation to account for intermolecular attractions. The real gas has a smaller pressure than the ideal gas. And so this is a subtracting term, subtracting another van der Waals constant times the square of the number of particles divided by the volume. And again, you do not need to know this equation, just that it exists. So if you take those two equations and combine them together, you get this, the van der Waals equation. Now, doesn't that make the ideal gas law look pretty simple? PV equals nRT. Now we're happy about that one. So if nothing else, this equation will make you feel better about the other equations. For B and A, you would have to look those up for the particular gas that you're doing a calculation for. And so here's a table from your textbook showing some different gases and their van der Waals constants for A and for B. And so you would just plug those in here. The units here are going to match up with the units of the ideal gas constant. And so again, you have to have your temperature in Kelvin, pressure in atmospheres, volume in liters, and amount of gas in moles. You might have to do a problem like that on a homework assignment, but I won't give you any of those on a test. There's no point. So if we look at these factors combined, we can see that the effects of interaction and particle size are different for different gases. So if we graph PV over RT, so that should equal N, the number of moles. So if we graph that for 1 mole of gas at different pressures, here's helium, neon, xenon, argon, and water. For an ideal gas, that's going to stay the same, right? For the real gases, it's going to vary. For helium, this curve is higher than the ideal gas constant. And so that tells us that the biggest factor in the deviation is the molecular volume, so the volume of the particles. Helium atoms have like almost zero attraction for each other. Things that dip below the line, like water molecules have pretty significant interactions with each other. And so the water molecules, the water curve is going to be below because there it's the force of attraction that's more significant.